When we consider sequences and series, we don't just look at APs, we look at GPs as well. So geometric progressions is the focus of our lesson for today. If you think back to APs, okay, the arithmetic progressions were all about addition. It was all about the letters A, N, and D for our common difference. That number that we added to each term to make the new term. We had our formula for a term. You should be familiar with UN equals A plus N minus 1 times D. And we had a formula for a sum. Sn equals half 2A plus N minus 1D. Half N 2A plus N minus 1D. So the idea is that is one type of sequence, so we can identify an AP. But we also have this second type of sequence that we're working with, the GP. And GPs are all about multiplication. So, setting ourselves up with 3 sequences again, we could have 2, 4, 8, 16, 32. We could have 20, 10, 5, 2.5, 1.25. We could have also 1, minus 3, 9, minus 27, 81. So we've got 3 different sequences here. They're all geometric progressions. Because what's happening is, in each of these, we are multiplying by the same value every single time. Okay, so 2 to 4 to 8 to 16 to 32, here we're going times 2. 20 to 10 to 5 to 2.5, we're going times a half. So in the same way that there was no subtraction when we talked about APs, it was all about addition, even if it was addition of a negative number. Here with the geometric progression, it's all about multiplication. There's no division. It is simply multiplication by a fraction. So we have our times 2, we have our times a half. And then this last one, which gets a bit more funky because our signs are changing. 1, minus 3, 9, minus 27, 81. This is a times minus 3. So we could multiply by fractions, we could multiply by whole numbers, we could multiply by an improper fraction, positive or negative, as long as it is the same value that we are multiplying each and every time. We've got ourselves a geometric progression. We do have something interesting we want to take note of now, because it's something we're going to hark back to later on in this lesson. If you look at sequence A and sequence C, we have a times 2 and we have a times minus 3. And if you look at the values in those sequences, you see that the values get bigger and bigger and bigger. We start at 2, we end up at 32, we're going to 64, 128, it's just going to go on getting bigger. From 1 to 81 times 3 times 3 times 3, it's going to go and get bigger and bigger and bigger. So if you're multiplying by a number that's bigger than 1 or less than minus 1, so large magnitude, magnitude being the size of the number. Okay, so multiply by greater than 1 or less than minus 1, magnitude of terms will, can't spell today, always increase. So the magnitude just refers to the size. It says, I don't care if you're positive or negative, I care that you are big. So 32 and minus 32 have the same magnitude. They're both 32. Okay, minus 100 and 100, same magnitude. The magnitude is 100. They're the same size. Okay, so if we're multiplying by anything bigger than 1, even if it's 1.1, 1.2, even if it's minus 1.5, if it's minus 15, okay, all of those sequences are going to give us values where that magnitude gets bigger. The contrast is this sequence B, because here we're getting smaller and smaller and smaller and smaller. Okay, so here we're multiplying by a fraction. a proper fraction. So we are between -1 and 1, not including -1 and 1, because that's just going to keep the same size. And we're not using 0, but we're talking here half minus a third, 2/7, 5/9. Okay, anything that's a proper fraction. Then our magnitude of terms is always going to decrease. As we go further and further into that sequence, our term size is going to get smaller and smaller and smaller. So it might be that they're positive numbers, it might be that they're negative numbers, irrespective of what it is, it's always going to get smaller, because each time we're taking just a fraction of that term, just a fraction of that term for the next term. Okay, so we've got quite a difference here between geometric progressions whose terms get bigger and geometric progressions whose terms get smaller. Two different types. Okay, but all with that same basic rule of we're multiplying by the same thing every time, term to term. So what are the special letters? For an AP, we had A, N, and D. Guess what? For a GP, not that much different. We still have A, the first term. We still have N, the number of terms, but not necessarily just all of them. I mean, we could use U3 as UN, and also it's also used as a term identifier. Okay, now we can't have D. D was a common difference, okay, all about addition. So we need something about a multiplication, and the letter we use for that is R. Our common, because it's the same one every time, ratio. So a GP has A, N, and R, and that's what you break down all of your formulas to when you're doing your summary of the sequence. So the common ratio is what we multiply by each time. So it's exactly the same as with the APs. We're going to be focusing on this concept of we want to work with a specific term. We want to work with a sum of a set of specific terms. Okay, so we still have formulas for those specific terms and sums. Okay, so UN was our term, our U3 third term, U10 10th term. So for a GP, we have UN equals A times R to the N minus 1. So we're using very similar. We got an A, same like an AP. We got an N minus 1, same like an AP. But we're working now with R. And we're working with multiplication because these sequences, these GPs, are all about multiplication. So we also have a formula for the sum of n terms. And in this case, it is A 1 minus R to the N over 1 minus R. But we have two different versions. A times R to the N minus 1 over R minus 1. Now these two are two versions of exactly the same thing. So you can pick one and always work with it if you want, or you can use either or. The reason behind having two is linked to this little relationship here. When our R has a big value, so like R is 2, R is minus 3, that large magnitude, then it sits more nicely if you use this formula here. So if you think about it, you would have 2 minus 1 on the bottom. So you have a nice big number. Okay? The other one we would normally use when r is a fraction. So multiplying by a proper fraction. And our terms are getting smaller. So if we had a half, if we had 5 ninths, if we had 2 sevenths, this is the formula that we would use. Because then again, we keep it positive. But as I said, both of these formulas are going to give you the exact same answer, so it doesn't really matter which one you use. It's not that you are wrong or right to use this one or the other one. My personal preference is that I actually just stick to this one, and you will see why just now when we talk about a very funky sum that we work with for our GPs. So that one for me is the one I remember, and it's the one I make sense of. And so it's the most straightforward one to use each time. But it is personal preference. You can go for whichever one you want to use. So just going to work through a couple of examples at substituting into these formulas to make sure that all is happy. So let's use our sequence A and B. So we had 2, 4, 8, 16, and 32. And sequence B was 20, 10, 5, 2.5, 2.5. So what are our important letters? A, our first term, equals 2. R, our common ratio, 4 divided by 2, which equals 2, or 16 over 8 or 32 over 16, any consecutive terms. Here, A equals 20, R equals 10 over 20 equals a half. So it's important to always keep track. So let's do the 20th term here. So U20, whoa, equals, okay, obviously far up, we don't want to be going through and multiplying and doubling everything all until we get to the 20th term. So we use our formula. We always go in for that specific term that we want to work with. U20 is A, so 2, times R, which is also 2, to the n minus 1. Okay, n is our identifier, it's at 20, so 20 minus 1 is 19. So 2 times 2 to the 19 is 2 to the 20, which is 104857.6. That's a big number. As we said, the numbers for this type of sequence are getting bigger and bigger and bigger. Let's look what happens here. U20 also again equals A is 20 times R is a half to the n minus 1 is 20 minus 1 is 19. So 20 times a half to the power 19, that gives us something very different. 0.0000381, which could also put as 3.81 times 10 to the 1, 2, 3, 4, 5 minus 5. So now you've actually got an application for standard form. It's not just some random way of writing numbers. So our numbers for this type of sequence, where we're multiplying by that proper fraction, getting smaller and smaller and smaller. And we're just going to take a moment here to make a note. Substitute all values. You Should know what's coming. In brackets. What this does is it means things like 1/2 gets raised the whole fraction to the 19. If you were to write something like 1/2 to the 19, this is 1 to the 19 over 2. It's not 1 to the 19 over 2 to the 19. Okay? You have to have those brackets in order for that 19 to go on the 1 and on the 2. Those brackets are critically important, particularly when you're working with fractions. And when you work with GPs, you do often work with fractions. So it is a very good habit to have in general, substituting all values in brackets. But you do not want to be throwing away marks because you don't write in a set of brackets when you're substituting a fraction, in particular when you're raising it to a power. So please make sure you substitute all your values using brackets. So we have the U20s. Let's try a sum. Let's try one of each. Okay, so S20 equals A, so 2, and we're going to use that version where our R is big so we can work with all the positives. So it would be R to the n, 2 to the 20, minus a 1 over 2 minus 1. So again, this is not a happy state of affairs. This is a happier state of affairs. Everybody in brackets, everybody was there, exponents in the right place, and all of the multiplications that should be done first will be done first. Okay, so we have all of this. We plug into our calculator just once, one calculation, and we would come out here with 209.7150. So on the other side, our S20 using the other version, A 1 minus R to the n all over 1 minus R. And again, we plug everything in one time and we get 39.999. So, thing is that when you're doing these questions, unless indicated otherwise, you should be rounding all of your answers to 3 significant figures. So this one becomes 40.0 to 3SF. Don't forget that 0.0, the 0.0 is important for that 3 significant figures. On the other side, historically, your answer would be left like that, but more and more, what we're seeing in the memos is that actually they would want this. They would also want that rounded to 3 significant figures because that is not a rounded off number, that is the exact answer. So yes, there's no ugly decimal places, but neither is it as neat and tidy as 3 significant figures. So my suggestion in this case would be to play safe, give your full whole number answer, but then also give it rounded with that indication that you've rounded to the 3 significant figures. Definitely when you have ugly decimals, there is no question about it, unless told otherwise, give it to 3 significant figures. So now we need to talk a little bit more about these 2 different types of sequence. So we can see what's happening here. I mean, we've got these enormous terms versus these tiny terms. We've got this enormous sum of 20 versus this not actually very big. I mean, 20 plus 10, that's already 30. Now you're telling me the sum of 20 terms is only 40 to 3 significant figures. So there is something fun going on here. And the difference here, technically terms, this is a divergent series and this is a convergent series. And when we have a convergent series, we have a very fun new formula to use with them. So let us just reiterate that and talk about convergent and divergent. So we have divergent GPs and we have convergent GPs. So a divergent GP is when that term value gets bigger and bigger and bigger. So we could have a little look at it like this. And we could say it's going to get bigger. So here we have term value, and here we have term number. So as your term number, 10th, 11th, 12th gets bigger, your value of your term gets bigger. Okay? We could also do this with a negative R. So in this case, we would have a term and we'd just be flipping between, because every time we multiply by the negative, we would change sign. So again, we have term number by term value. And so this is our case where we said R is less than -1 or R is greater than 1. It's those large magnitude common ratios. For our convergent GPs, things are a little bit more interesting. Same graph, term value against term number. So here, R is little, so we're getting smaller and smaller and smaller. So -1 less than R less than 1, but R doesn't equal 0. So our proper fractions. Same thing, even if it's a negative fraction, it's going to look slightly different, but it's also going to get smaller each time. Term number and term value. And this line in the middle or at the bottom is actually 0. So you can see that our convergent series, convergent GPs, as we get higher and higher on our term number, our term value gets closer and closer to 0. And this means that we're adding virtually nothing to 3 significant figures. We're adding 0. And that means that we can have real fun with our sum. When we're adding such minuscule values, they have no effect on the sum, and we can actually sum to infinity. So our convergent GPs will have a sum to infinity that we can calculate. And it's really, really, really cool, because it is very simply the sum to infinity equals a over 1 minus r. So now you know why it is that I like the one of those two sums, because I have an a over 1 minus r. I can remember that for a sum to infinity. So if I'm not doing a sum to infinity, it's just a 1 minus r to the n added in on top. But if we have one of these convergent GPs where those term values are getting smaller and smaller and smaller because we've got that proper fraction that we're multiplying by all the time, then we can calculate the sum of an infinite number of terms. So if we have a think about our 3 original sequences, we had sequence A, which was A equals 2, and R equals 2. We had sequence B, which was A equals 20, R equals 1/2. And we had sequence C, which was A equals 1, R equals -3. And now you can see that these two, their technical terms, we would call them divergent series. Term values are always getting bigger in magnitude. There is our fun one. When R is a proper fraction, we have a convergent series, and we can therefore do sum to infinity as a calculation. So how would we do it? For this one in particular, sum to infinity, very simply, equals a 20 over 1 minus 1/2, which is 20 times 2, which is 40. Funnily enough, very, very similar to that sum of 20 terms that we got for the same sequence. So it's the same thing as with our APs. We can use all of our formulas, our UN, our SN, and now our sum to infinity in any direction. We can use them to calculate any missing piece. We can calculate a sum or a term, or we can calculate an A, an N, or an R. We're working in all the different directions. So what is important is that you get very familiar with all of the formulas and make sure you're doing lots of questions so that you've got lots of practice using those formulas. But then also be familiar with these restrictions on when you can use the sum to infinity formula, because they can ask really lovely questions about giving you information about R rather than R itself, and building inequalities and all sorts of fun and games. But you would have to be familiar with that fact that R must be between -1 and 1. So make sure that you're happy with the concept of divergent and convergent series, as well as all the other things that you're working with for GPs.